Hello, and welcome to some more remote learning. Today we're going to do more on power series, and I should really rename this worksheet because we're going to go over combining power series through sums and differences, multiplication by a power, and composition. And then we're also going to dive into relating power series through differentiation or integrating. So let's dive into combining power series. Now we're going to be combining power series again through sums and differences, multiplication by a power, or composition. So we're going to suppose the power series, the summation of c sub k times x minus a to the k, and the summation of d sub k times x minus a to the k. So those two separate series converge to f of x and g of x respectively. And to simplify this down, just to make it a little bit easier when we're writing out these theorems, I'm going to say that we're centering each of these at 0. So I'm going to say c sub k times x to the k and d sub k times x to the k, those series. Which these rules will still apply when we're not centered at a, it's just going to be a little bit more manipulation for some of that algebra. So I'm just going to center it at 0 for the sake of this video. So we're going to have that c sub k times x to the k, that series converges to f of x, and we're going to say that summation of d sub k, x to the k, converges to g of x. And those series are going to converge to f of x and g of x on some interval. So going over the sum and difference, well, it's kind of like what it says. We're going to add or subtract those series. So I'm going to say the summation of c sub k, x to the k, and we're going to add or subtract, because we're doing the sum or difference, of the summation of d sub k times x to the k. Now remember, c sub k and d sub k are just going to be coefficients of that x to the k. And if we're on the same interval, we can write this as the summation of c sub k plus or minus d sub k times x to the k. And this converges to, well, if we remember, each of the individual series converge to f of x and g of x respectively, so when we sum them or subtract them, it's going to converge to f of x plus or minus g of x. Now for multiplication by a power, we're going to define some other constant. We'll call it m. And we're going to say that m plus k has to be greater than or equal to 0. This is just so we don't get a negative exponent and then have to worry about flipping fractions and such. So it's only going to work for where m plus k is going to be greater than or equal to 0. So if I have some x to the m and I'm multiplying that by my series, I'll multiply that by my series c sub k times x to the k. Well, if we brought this x to the m within our series, we would get the summation of c sub k, that coefficient, times x to the, remembering those exponent rules, k plus m. Because I have the same base, I can combine those exponents through addition. So this series converges to x to the m times f of x. And this is for values when x doesn't equal 0. If x does equal 0, then we're going to converge to the limit as x approaches 0 of x to the m times f of x. And that's only in the case where x equals 0. For all else, we're converging to x to the m times f of x. And lastly, we're going to talk about composition. So for composition, let's say that we have some function, I'll call it g of x. We have some function g of x that's going to be b times x to the m. So g of x is going to be b times x to the m. So m is going to be some positive integer in this case, and b is not going to be 0. If we're looking at our power series c sub k, but now we're doing our function g of x raised to the k, as opposed to doing x to the k, we're doing g of x to the k, then this is going to converge to the composite function of f of g of x. Because notice, c sub k times x to the k converges to f of x, but as opposed to plugging in x, we're plugging in g of x for x. So now we have f of g of x that our new series is going to converge to. Now let's dive into some examples applying the theorems above. So for example 1, it says to use the geometric series f of x equals 1 over 1 minus x, which is equal to the summation from k equals 0 to infinity of x to the k for the absolute value of x less than 1. So that's when that series converges, because we can only apply those theorems when we're converging. And we're going to use that to find the power series representation for the following functions centered at 0. And we're going to give the interval of convergence for that new series. Now, if I was to cover up either part of this, so let's go ahead and cover up that f of x equals 1 over 1 minus x, what do we have here? We have a geometric series. And remember, a geometric series converges when the r value, or in this case, our variable x, is between -1 and 1. And you can see we specify that. And if our geometric series converges, what does it converge to? Well, that's our a over 1 minus r, right? But in this case, our r value is x, and our a value is just going to be 1. So you can see 1 over 1 minus x is what my series is equivalent to. That's my f of x. So if I have a, which says x squared over 1 minus x, I'm going to rewrite this as, well, I can pull this x squared out in front, and I have my 1 over 1 minus x here. X squared times 1 over 1 minus x, we know exactly what 1 over 1 minus x does. That's our geometric series. So I have this is x squared times the summation from k equals 0 to infinity of x to the k. And using which theorem above? Using that second one, the multiplication by a power. All I'm doing is multiplying this series by x squared. So that allows me to bring that x squared inside my summation. So I have the summation from k equals 0 to infinity of x to the k plus 2. So you can see I'm adding those exponents, x to the k plus 2. That's the power series representation of our original function. X squared over 1 minus x equals the summation from k equals 0 to infinity of x to the k plus 2. But we have to give an interval of convergence because this is only true when our series converges. And we did not manipulate our r value from above, so this is still going to converge when our absolute value of x is less than 1. So as long as x is between -1 and 1, our series is converging, because our r value in this geometric series is equal to x, and r converges between -1 and 1, so the series will converge when x is between -1 and 1. Let's go ahead and zoom in and go over b. b is 1 over 1 minus x to the 4th. So if we have 1 over 1 minus x to the 4th, if you remember, our f of x is equal to 1 over 1 minus x. But as opposed to plugging in an x, we're plugging in an x to the 4th. So this is equivalent to f of x to the 4th. So if our series of 1 over 1 minus x is equal to the summation from k equals 0 to infinity of x to the k, and that's when we're converging, so when x values are between -1 and 1, then f of x to the 4th is going to be equivalent to the summation from k equals 0 to infinity of, I'm going to plug in x to the 4th where I see x. So this is x to the 4th, all raised to the k. So here's our power series representation of 1 over 1 minus x to the 4th. And this is true on that interval where we're converging. So notice now that my r value is x to the 4th, no longer an r value of x when talking about a geometric series. So because r equals x to the 4th, we're converging when, remember, it's that absolute value of r is less than 1, so that's when the absolute value of x to the 4th is less than 1. Or we can say when that absolute value of x is less than 1, because 1 to the fourth is 1 and negative 1 to the fourth is 1. So here in part B, we actually use the composition part of that theorem because we plugged in a function of x in for x. And then lastly, part C, which is very similar to part B. Remember that f of x equals 1 over 1 minus x, and that's equivalent to the summation from k equals 0 to infinity of x to the k. And again, that converges when x is between negative 1 and 1 because it's a geometric series. As opposed to plugging in an x, though, I'm plugging in a negative 6x because this is equal to f of negative 6x. You can see that if I took a negative 6x and plugged it in for x, I'd get 1 over 1 minus a negative 6x, which is 1 over 1 plus 6x. So I'm taking negative 6x and plugging it in for x. And the same applies to my power series. I'm going to have k equals 0 to infinity of negative 6x to the k, which if I wanted to, I could pull that negative out. So going from k equals 0 to infinity of negative 1 to the k times 6x to the k. So you can see that it's an alternating series. But besides being alternating, it's actually just a geometric series with an r value of negative 6x. So if our r value is equal to negative 6x, remember we converge when the absolute value of r is less than 1. So we're going to converge when the absolute value of negative 6x is less than 1. So I can divide that 6 over, so that's going to be when the absolute value of negative x, or simply just the absolute value of x, is less than 1/6. So we're converging as long as x is between negative 1/6 and 1/6. And you can see if I had a negative 1/6 in for x, I would get a positive 1. And if I had a positive 1/6, if I plugged that in for x, I would get a negative 1. So we're converging as long as x is between negative 1/6 and 1/6. And that's using our knowledge from geometric series. Feel free to use those concepts we recently learned for figuring out what a power series converges to. If you do the root or ratio test, you'll be able to find that same exact interval of convergence and your radius of convergence, which I would have had to have done if this wasn't necessarily a geometric series. Because if this wasn't a geometric series, I would not have been able to rely on that r value, so I would have had to move on to the root or ratio test to figure out my interval of convergence and my radius of convergence. Let's move on to the next part of this video, where we're going to go over differentiating and integrating power series. Now for the really fun part. So for differentiating and integrating power series, again, let's just suppose that we have some c sub k times x minus a to the k, that series, and let's state that it converges for the absolute value of x minus a is less than r, and defines a function f on that interval. So that series is essentially equal to some f of x. Now, we're allowed to differentiate that function f of x, and in turn also differentiate the series that f of x is equivalent to. So if I take f prime of x, I'm going to then differentiate my c sub k x minus a to the k, that series, with respect to x. So I'll just have the summation of c sub k is just a coefficient, so it's just a number, and we'll drop that exponent down in front. So this will be k times c sub k times x minus a to the, now remembering the power rule for the derivative, will then decrease that exponent by 1. Now integrating, well, we're going to take the integral of f of x. So the integral of f of x with respect to x, now we're going to integrate this series. So again, that will be increasing our exponent by 1 and dividing by that exponent. So this will be the summation of c sub k times x minus a to the k plus 1 all over k plus 1. And we're going to add some constant c since it's an indefinite interval. And just a side note, because this will come up later when we get into our examples, we cannot forget the chain rule when differentiating and integrating. So let's go ahead and jump into my first example, my differentiating example. So I said let f of x equal 1 over 1 plus 6x. So even if you couldn't see all of this over here, we can see that that's a over 1 minus r, where r is going to be a negative 6x. So this is negative 6x to the k, r to the k. So it's some geometric series. And it's the same thing we did up above in example C. I took that same function, so again, we know it's geometric, and we know it converges on the interval from negative 1/6 to 1/6. And I wrote out the terms of the series because in part A, I want to determine the power series representation of f prime of x by differentiating the terms of f of x. So first, let's see what f prime of x actually is. F prime of x is going to be equal to, if we rewrote f of x as 1 plus 6x to the negative 1, drop that exponent down in front, that'd be negative 1 times 1 plus 6x to the negative 2, here's the chain rule part, times a 6. So our derivative is equal to negative 6 over 1 plus 6x squared. Now, if you were given a function like this, there would be no way to use the combining power series theorems above to help us figure out what the series is equivalent to. However, we know it's the derivative of f of x, and because it's the derivative of f of x, if we were just given this series and told to find a power series representation of it, we could then differentiate our series for f of x. Alright, so what I'm going to do is I'm going to differentiate each of these terms in the series, and I think it's easier writing them out so we can see. So I'm just going to rewrite this in a different manner. So we're going to have 1, so then negative 6x is going to be a negative 6x, so I'll write that as subtracting 6x. And then we'll have a positive, because a negative 6 squared will be a positive, so that'll be 6 squared x squared. And then we'll have a negative again, because a negative cubed is still a negative, so I'll subtract 6 cubed x cubed. And then if we continued on, then we'd be adding 6 to the 4th, x to the 4th, and so on. So what I want to do with this is I want to differentiate each of these terms. So differentiating 1, that goes to 0. The derivative of 6x is going to be 6. The derivative of 6 squared x squared, dropping that exponent of 2 down in front because 6 squared is just a coefficient, so it's just out in front, just some constant. That will be 2 times 6 squared x. And then I'll be subtracting 3 times 6 cubed x squared. And then I'll be adding 4 times 6 to the 4th x cubed, and so on. Now I wrote it out like this so that we can pick up on our pattern, because we're trying to find the power series representation of our derivative. This is what f prime of x is equal to as we write it out. So finding that derivative, taking the derivative of each of my terms in my series, I'm now going to find that pattern to write it as a summation. So we're going to have the summation from k equals 0, we'll start at that starting index of 0, to infinity of, well, notice I have 0 in my first term, and then if I'm looking at this 2, 3, 4 pattern, that's kind of like a k, because this would be k of 0, k of 1, k of 2, k of 3, 4, and so on. So I have my k. That takes care of 2, 3, and 4. Now I just have to figure out those 6's. So notice I have a negative 6 and then a positive 6 squared, a negative 6 cubed, and then a positive 6 to the 4th. So I'll leave that negative with the 6, and that will be raised to the k. Because this is negative 6 to the 0, which is 1, and 0 times 1 is 0. This is negative 6 to the first, negative 6 squared becomes a positive, and so on. And now all I have to worry about is my x, which my x has an exponent of 1 in that third term, an exponent of 0 in the second term. So that means it'll probably have an exponent of a -1 in my first term if I keep that pattern up. So this will be x to the k minus 1. So this is our power series representation of that derivative. And we can do the same exact thing by just differentiating the series we were given with. Because remember, f of x is equal to 1 over 1 plus 6x. And that series, when it converges on that interval from -1/6 to 1/6 for x, that series representation is k equals 0 to infinity of -6x to the k. I can find that power series representation of the derivative just by differentiating this series. So if I have f prime of x, we said that's going to be -6 over 1 plus 6x, that whole entire quantity squared. Differentiating this, I'll have my summation from k equals 0 to infinity of, dropping my k down in front, that'll be -6x to the k minus 1, decreasing that exponent, but remember, chain rule is important here. Then I have to multiply by the derivative of my inside, which is multiplying by a -6. Now let's go ahead and simplify this down a bit, distributing this k minus 1 into -6 and into x. So when I distribute that, I'll get the summation from k equals 0 to infinity of k times -6 to the k minus 1 times x to the k minus 1, all multiplied by -6. But think about this. If I was then to break up this -6 to the k minus 1, that is equal to -6 to the k over -6 to the positive power of 1, because it would be -6 to the k times -6 to the -1, which would get moved into the denominator as a positive. And if I have -6 in my denominator, and I have a -6 in my numerator, those will get canceled out to leave me with does it look familiar? K times -6 to the k times x to the k minus 1. It's the same exact thing we got up here. So with that being said, either way of trying to find that power series is perfectly acceptable. You can take the derivative of each of the terms and find the pattern, or just take the derivative of that series. Now the next part of this says that we're going to state the interval of convergence. So if we're looking at k times -6 to the k times x to the k minus 1 and figuring out the interval that it converges on, if it does converge, which means that we are indeed equal to this function when we converge, we're just going to do either the root or ratio test. And let's go ahead and do the ratio test because I think you guys need some practice on it. So I'm running out of room because I wrote a little big, so I'm just going to slide my page over and do my ratio test over here. Now remember, the ratio test is going to be the limit as k approaches infinity of the absolute value of my a sub k plus 1 over my a sub k. So my a sub k plus 1 is going to be k plus 1 times -6 to the k plus 1 times x to the k plus 1 minus 1, and that's all over k times -6 to the k times x to the k minus 1. Now, a bunch of things are going to cancel out for us as we simplify this down. So I'll have the limit as k approaches infinity of, I'll leave k plus 1 as is, but -6 to the k plus 1, I'll write as -6 to the k times -6. And then x to the k plus 1 minus 1 will be x to the k. And that'll be all over k times -6 to the k times, I'll break up this x to the k minus 1 as x to the k times x to the -1. And we're taking the absolute value of that. You can see that -6 to the k cancels out, -6 to the k cancels out, x to the k, and x to the k. So I'm left with the limit as k approaches infinity of the absolute value of k plus 1 times -6 times, I'm going to flip this negative exponent up into the numerator. So that'll be times all over k. which from that interval convergence video, we know that we can pull the absolute value of that negative 6x out in front of our limit because it's not involved when we're plugging in for k. So if we have the limit as k approaches infinity of k plus 1 over k, this limit's going to be equal to 1. So we'll have 1 times the absolute value of negative 6x, which is the absolute value of negative 6x. And remember, we did what test? The ratio test. So we're going to calculate for when negative 6x, that absolute value is less than 1, which occurs when the absolute value of x is less than 1/6. So that's going to be our interval of convergence. And I would go ahead and check your endpoints as well to see if we are actually converging at those endpoints. Are we including negative 1/6 and 1/6 in our interval or not? So go ahead and try that on your own. Now I'm pretty sure it's going to diverge at each of those endpoints, but for the sake of time, let's move on. In our next example, we're going to be integrating. So we're doing an integrating example. And again, I'm going to use part C from up above when we were just combining those power series. So we're dealing with 1 over 1 plus 6x again. Now we're going to determine the power series representation of the integral of f of x dx by integrating the terms in our series for f of x. Kind of the same process for our differentiating example, except now we're integrating. So let's go ahead and see what the integral of f of x would be. Well, f of x equals 1 over 1 plus 6x. So if we integrated that, the integral of f of x dx, doing u sub in my head, if u was equal to 1 plus 6x, my du would be 6. So when I integrate f of x dx, I would have to integrate 1/6 times 1 over u du, which I know is 1/6 times the ln of u, which will just be the ln of 1 plus 6x all over 6. So if you need to write that u sub out, feel free to, or just go ahead and double check by taking the derivative of the ln of 1 plus 6x over 6, remembering that chain rule. So now let's individually integrate each of my terms. And again, I'm going to write this to make it a little bit easier to line up. So we have 1 plus negative 6 to the first, x to the first. Then we have a positive 6 squared x squared, a negative 6 cubed x cubed, and then we're adding 6 to the fourth, x to the fourth, and this pattern continues on. Now, integrating 1, we'll get x. Integrating a negative 6x, we'll be subtracting 6x squared over 2. And then integrating 6 squared x squared, we'll get 6 squared x cubed over 3. And then we'll get 6 cubed x to the fourth over 4, and that will be negative. And then we'll be adding 6 to the fourth, x to the fifth over 5. So you can kind of see the pattern already. We're going to have the summation from k equals 0 to infinity of, well, let's take care of x first this time. Here we have x to the first, x squared, x cubed, x to the fourth, x to the fifth. That's like x to the k. Although if I do x to the k, I don't necessarily want this to start at an index of 0, so I'll move this to start at an index of 1. So then I'll have x to the k. And along with my x to the k, notice that I'm positive, then I'm negative, then I'm positive, then I'm adding a negative, then I'm adding a positive, and so on. So I need some negative to a power to get that oscillation. And that's going to be a negative 6. So I'm going to take my negative 6 and I'm going to raise it to some power. I want that to be negative 6 to the 0 when k equals 1. So I'm going to do negative 6 to the k minus 1. So we have negative 6 to the k minus 1 times x to the k. And you can see I did k minus 1 because when I plug in 1, I get 0. Negative 6 to the 0 is 1. When I go to a k value of 2, I get negative 6 to the 2 minus 1, which is negative 6 to the first, which is indeed that negative 6, and so on. So feel free to double check, plugging in a couple more k values. But lastly, I have to take care of that denominator. So my first term is over 1 essentially, and then over 2, over 3, over 4, and so on. So that's going to be all over k. And I know I can simplify this a little bit further, because if I split up this negative 6 to the k minus 1, I'll be able to combine my negative 6 to the k with my x to the k. So I'm going to write this as the summation from k equals 1 to infinity of negative 6 to the k times negative 6 to the negative 1 times x to the k all over k. Now I'll be able to combine my negative 6 to the k with my x to the k, but my negative 6 to the negative 1 is going to drop down into my denominator. So I'll rewrite this as negative 6x to the k all over a negative 6k. Or I'll go ahead and put this negative right here, just to make it a little more clear. Or I can even pull that negative out in front of my series. Either way of doing it, it's fine. So this is a good power series representation of the integral of f of x. Now, let's do it by just integrating the series. So again, f of x was equal to 1 over 1 plus 6x. When we integrated f of x dx, we got the ln of 1 plus 6x all over 6. So now all I have to do is integrate that power series from k equals 0 to infinity of my negative 6x to the k. So if I was to integrate that series, negative 6x to the k, I'm going to increase my exponent by 1 and then divide by it. So that'll be negative 6x to the k plus 1 all over k plus 1. But remember, this was a negative 6x to the k. That's like saying u to the k. So if u is 6x, then my du would have been negative 6. So when I integrate, I just got to make sure that I divide by negative 6. So this will all be multiplied by a negative 1/6. And this was from k equals 0 to infinity. Now you see, since both of my k values have a plus 1 with them, all I can do is shift that index and start at a k value of 1, so then I don't have to do k plus 1 within there. I can just do k. So shifting my index, I'm also going to have to change my k plus 1s. So by shifting it, I get the summation from k equals 1 to infinity of negative 6x to the k all over k times negative 1/6. But I'll pull that negative out in front and put my 6 in the denominator. So negative 6x to the k all over 6k. And again, you can see that I got the same exact series as above. The opposite of negative 6x to the k over 6k. Negative 6x to the k over 6k. The same thing as above. Either way of integrating is fine. And remember, this is going to be equal to that integral. So this is equal or equivalent to the ln of 1 plus 6x all over 6. However, this is only true for the x values that make the series converge. So on your own, I want you to find the interval of convergence for this and test your endpoints. And what's cool about this is that you're going to get one endpoint that diverges, but the other endpoint is going to converge. So you're going to have one of your endpoints included in your interval of convergence. So go ahead and find out which endpoint that's going to be. But for now, let's extrapolate a little bit further on this and determine the power series representation of some new function, the ln of 1 plus 5x. Well, the ln of 1 plus 5x looks really similar to the ln of 1 plus 6x over 6. When we have x values that make our series converge, the ln of 1 plus 6x all over 6, that's going to be equal to our series from above. But what I'm going to do is I'm going to pull out that negative 1/6 out in front, just leaving my variable and my k values inside. So I'm going to have negative 1/6 times the summation from k equals 1 to infinity of negative 6x to the k all over k. Now what I want to do is I want to figure out what my power series representation of the ln of 1 plus 5x would be. So these two are equivalent for where our series converges. So what I'm going to do is I'm just going to simply multiply both sides by 6. And when doing that, my 6 cancels out over here to leave me with the ln of 1 plus 6x. And that's going to be equal to, the 6's over here will cancel out. That'll be a negative summation from k equals 1 to infinity of negative 6x to the k all over k. So now we're even closer to that ln of 1 plus 5x, because if I just change this 6x to be a 5x, I'll be at the ln of 1 plus 5x. That's just as simple as changing the input in my series. So the ln of 1 plus 5x is going to be equal to negative summation from k equals 1 to infinity of negative 5x to the k all over k. That's what the ln of 1 plus 5x will be. What would you do if you had the ln of 1 minus x? Well, that's just going to be equal to the negative summation of k equals 1 to infinity of, now as opposed to plugging in a negative 5x, we're plugging in a positive x. So that'll be x to the k all over k. This should be very familiar because it's an example in your book, so you would have found that when you were reading your textbook, and it's also a common example for expressing power series based on integrating. So once you find your relationship between some function f of x and g of x, either by differentiating or integrating, there's just a few small manipulations that need to be made to create that power series representation. Hopefully you found this video helpful. If you have any questions on the examples above, please feel free to leave it in the comments. Also, don't forget, we didn't quite finish figuring out the interval of convergence in part B of both our differentiating example and our integrating example. So go ahead and find each of those intervals of convergence, making sure to test those endpoints, and let me know what you get. Good luck, and see you next video.